So hello everyone. So let's start our new unit. In the last unit we have discussed about the DC characteristics of the CMOS inverter. Now in this unit we are going to discuss the dynamic characteristics, or what are also called as the switching characteristics. So static characteristics, which we have talked in the last class, were important to find the threshold voltage and the noise margin. So to find the noise margin, what we have done is we have determined VIL and VIH. But static characteristics are also important to determine the noise margin and the threshold voltage. But the switching characteristics are more important for any circuit, and basically they are more important for CMOS inverters. So for CMOS inverters, what we do is when we have to determine the switching characteristics, we have to find some parameters for it, okay, the related parameters. But before moving to the related parameters, we will define some of the terms, and then we will like to calculate the related parameters like the delay. Okay, the most important thing for the inverter is the delay. Okay, the propagation delay, the time which the signal takes to propagate from input to the output. So that much amount of time is like required, minimum time is required, whatever minimum time is required, so that is called your propagation delay. So that we have to find. So how to find that? Because that will be considered as the switching. So you see, and apart from that, till now we have considered that our input waveform is an ideal waveform. That is, it doesn't have any rise time or the fall time. But the practical waveforms have some rise time as well as the fall time. So to include that as well in the calculation, we have to determine the rise time and fall time also. So if you are simulating the things, then it will be very easy for you to determine that rise time, and once you'll get the definition, as you know the definition of all these things very well from your previous courses, so it is not difficult to find them, but being this as an introductory course, we will define those things in this class. So the aim for our today's class will be to derive the equation for the delay current, okay, the propagation delay time, sorry. So we have to derive the propagation delay time, then we have to determine the equations for rise time and fall time. So this is the aim of our today's class. So let's move on. So let's first of all define some of the things. So you see, whenever the transistor will switch, as you know that the delay will come because as soon as you apply some input, the output you will not get the output at the same instant. That output will be after some time. So that much time which is elapsed between the input, the change in the input happens, and when the change in the output is also seen, okay, the same change in the output is also seen, so that much time is called your propagation delay. So that propagation delay, whenever you talk about, so that propagation delay comes because of your impedance. Okay, so impedance, when we talk about, so it is basically R, L and C. Okay, so combination of this is called your inductance. But in this cases, as you will see, that the amount of inductance is not very much, and it is, I mean, if you operate the circuit at very high frequency, then there will be some inductance, but that can be ignored at the operatable frequencies. So we only talk about the capacitance. Okay, so the capacitance in the circuit is because of the many parameters, many things, the parasitic capacitance of the device itself, or you can talk about the parasitic capacitance of the interconnects, or the parasitic or the capacitance of the next stage. So if you combine them, the various type of capacitances, and assume that they are all combined in what is called as the load capacitance. Okay, so if you combine all of them in one capacitance and consider it as a lumped parameter, and that C load, the load capacitance if we assume that all the capacitances which comes into picture, okay, are included in the C load, okay, or the load capacitance, then considering this, we can like calculate the impedance of the circuit, or that circuit will give you some impedance, okay, it will feel some impedance. So that opposition to the current will be not because of the inductance but because of the resistance of the running wires, of the interconnects, of the devices itself. So you see there will be some resistance and the capacitance. So that propagation delay basically comes because of this RC circuit, which forms because of our this devices and the parasitic capacitances of the device, the next stage, and the interconnects. Okay, so whenever there is a formation of this impedance R and C, let's say, so there will be always some delay. The output will respond after some time. And as will talk about the switching characteristics, so this RC will play a very important role. So we have to see that how to determine these things. Okay, so you see this the switching speed of the device or any circuit will depend upon your load capacitance or the combination of all these capacitances. Okay, so that is important. So that is why we have to minimize this capacitance as much as possible. So we'll try to minimize the capacitance. Okay, then we cannot increase it too much, although there are some advantages of increasing the capacitance, but it will be the delay will be increased because of this. Okay, and you will see later on that the power dissipation will also increase, so we'll try to minimize that. Okay, then the other important thing is your rise time and the fall time. So rise time, as we already know that rise time and fall time are nothing but the time which the waveform takes to rise from 10% to 90% or to fall from 90% to 10%, okay, of its steady value. So whenever you define the rise from 10% to 90% of the steady value, then you call it the rise time, whereas if you define it as the fall from 90% to 10% of the steady state value, then you call it the fall time. Okay, so this is what it is. And propagation delay. So as I have told you the propagation delay, what it is, but we need some mathematical exact definition for it. So it is nothing but how you define it is the time difference between the input transition of 50% input transition and the 50% transition of the output level. Okay, so that period is called your this propagation delay. So we'll see in the next slide that how it looks on the waveform. So you see propagation delay, if you talk about, so let's say in this waveform you can see that we can see the ideal waveform as well. This is your ideal waveform, the rectangular one, and whereas there is the other waveform which is having some slope. Okay, so the first waveform do not have any rise time or fall time, whereas the second waveform have some rise time or the fall time. So the initial discussions, first of all we will discuss the circuits without the rise time and the fall time of the input waveform. So we'll consider the input waveform without any rise time or the fall time, but later on we can include it. Okay, for simplicity of the calculations, we'll consider that the input waveform do not have any rise time or the fall time. Okay, but later on we will include it in the formula. Empirically it is done, and then we will see that how it looks like. But if you want to let's say define the total propagation delay, so you can see in this equation that your total propagation delay is defined by something which is tau phl plus tau plh upon 2. Okay, so the average of this two. So we have to define the propagation delay of tau phl is the propagation delay when this output signal is falling from high to low. Okay, so it is falling of the output waveform from the high level to the low level, but it is not exactly low level. So we are talking about tau phl. So tau phl is the transition from the time which is elapsed between the 50%, okay, 50% of the input to the 50% transition of the output. So that much time is called the tau PHL. Similarly, on the other side, if you will see that the rise time, the rise of the waveform, it's not the rise time, but it is the output is rising. So the time duration in which your the output, the input waveform is falling, and the 50% transition of that falling age of the input waveform to the rising age of the output waveform, 50% of the rising age of the output transition waveform. So you see that duration will be denoted by tau p LH. So if we determine them separately, they can be, this tau PHL and tau PLH may be equal, or in the most of the cases you will see that they are not equal, they are different. But if you make certain arrangement, they can be equal as well. Okay, so whatever their value is, whether they are equal or non-equal, then if you want to determine the total propagation delay, so then the total propagation delay or the average propagation delay, the better term will be the average propagation delay. So average propagation delay, if you want to determine, so it is nothing but the average of tau PHL plus tau PLH by 2. Okay, so this is what we have to see. So you can see that for a single waveform, this is your propagation delay. Okay, now if let's say you have simulated the circuit and you can directly see this output waveform, then you can also measure the time difference. So let's say the 50% transition time of the output waveform is denoted by T1, and the 50% transition of the input waveform is denoted by T0. So then you can write tau PHL is as T1 minus T0. Whereas similarly, if you denote the on the rising edge of the output, you denote the same points of the 50% level of the input and output as T2 and T3, then you can determine tau PLH as T3 minus T2 as well. Okay, but if you want to determine these things theoretically, then we can determine it by some formulas as well. So this is what it is, we can see. So tau PHL and tau PLH are two terms. They can be derived by simulation directly, by observation on the waveform, but we can derive them as well. So we'll see that. But let's say if I try to write the 50% level of this output waveform, so how I can write that 50% level, because this 50% level is useful for us to denote in terms of VOL and VOH, because later it will be used. So you see, we have already defined in our previous unit that what is our VOH and what is our VOL. So VOH is the maximum value of the output, okay, and VOL is the maximum value of the input, which is like defined as the low on the lower side. Okay, so you see VOL and VOH we already know. Okay, so you can revise it from the previous thing. So if you want to determine the 50% of this value, so it is nothing but you can take it as VOL plus VOH by 2. Okay, so you see this is what it is. So you basically take the lower side and then the difference of the upper side and the lower side, okay, and half of that, and then when you calculate it completely, so you'll get it half of VOL plus VOH. So it is a very simple thing. So this is how we can determine 50% level. Okay, now let's determine the rise and fall time. So rise and fall time is nothing but let's say, as I have already told you, it is the transition from 90% to 10% and or from 10% to 90% of the steady state value. So if we denote them here, then we can denote that T fall or the fall time is your TB minus TA. If this times are TB and TA, so you can denote them as you can write it as TB minus TA, or you can write it as TD minus TC, right? Whereas if you want to determine it in terms of VOL and VOH, then obviously what we want is, let's say VOL is our initial value and we want the 10% level. So 10% level of our this waveform will be the higher side is VOH, lower side is VOL. So we want the 10% level. So 10% level is difference of the this higher value VOH, which is here VOH. So VOH minus, let's say VOL is somewhere not here, but it is VOH is here and VOL is somewhere little bit above the x-axis. Okay, so you see VOH minus VOL, and then 10% of this we have to take, okay, when we are talking about this value, and then add that to the VOL. Okay, so this is how we get the 10% of the transition. Okay, this is what we want, and similarly the 90% of the transition. So this is how you define the rise time and fall time as well. Then once this is defined, now we have to calculate the delay. So delay is not difficult to calculate. We can calculate it with multiple methods, but first we will see the easier one, and then later on we will see the little difficult one, but which will give you more accurate result. Okay, so this is the first one is simpler one, but it will give you approximate result, more approximate. The other method is also gives you the approximate result, but it is more accurate than the first one. So first we will see the approximate method, the very crude method, and then we will see the other method. So you see our basic formula of capacitance, if you write, so we know that our capacitance is nothing but Q is equal to CV, and Q is nothing but I into tau. Okay, so Q is, current. How you define current? It is charge per unit time. So if you multiply, okay, current into time, so you will get the total charge. So the same thing is written here. So tau PHL in terms of C and I. So this is what is written. So TPHL, if you write, so it will become the load capacitance and your change in voltage. So change in the voltage. So it is high to low. So the voltage will change from high to low. Okay. So our input voltage is changing from high to low. So del VHL, we write it like this. So how we'll write it? VHL input is changing from high to low. So initially let's say it is high 50% VOH, and then it is changing. So lower side, if you talk about, so LH is your 50%. Okay, so of that. So as the input do not have any rise time or the fall time, so we are assuming that at that same instant, previously it was 0 VOL, but later on it becomes VOH. So we have to find the things after transition. So that's why we are taking the value VOH and not the VOL. But we have to take the other value, which is the 50% value. So let's write the 50% value of the output, which we don't know here. So we have written the 50% and then the average current. So our aim will be to determine the average current, and then once you will determine the average current, we can substitute that in this equation and can easily find tau PHL. Okay. Similarly, on the same lines, you can find tau PLH as well. But the point is how to determine the average current. Whenever you have to find the average current of the waveform which is transiting from high to low or from the low to high. So it is the average current of your drain current. So average of drain current in two situations. So input is like changing. So input is changed from 0 to VOH. So input is becoming VOH. Now once the input becomes VOH, then initially when the input was VOL, at that time output was VOH. Okay. Now when the input also changes to VOH, output won't suddenly become VOL. It will be initially remain to VOH. So the initial condition will be V in is equal to VOH and V out is equal to VOH. Okay. So this, at this situation, how our devices are working, first we have to see that, and according to that we have to find the drain current equation of the device. Okay, if it is working in the saturation region or the linear region, so you have to consider that particular case and whatever the case is, and accordingly you have to use the current equation. Okay, the point is that in the second case, the average of what? First term I have explained. The second term is the end of this transition, end of the propagation delay time. So we define it as when V in is like remains VOH only. So now V in is not changing, but V out is changing. So V out was initially VOH, but now it becomes 50% of that. Okay, so the steady state value. So that time. So again at this instant we have to find that our devices are working in which region. So in whichever region they are working, we have to substitute the current equation for that region and then solve it. Take the average of this two. Same thing we have to follow when we try to determine, when we will like to determine the average current for low to high case. So this is how you determine the average current, and once you determine the average current, then you can substitute that current into the equation of tau PHL or the tau PLH as per your requirement and can find that. Okay, now let's see, this was the first method. Okay, now let's move on to the other method, which is, as I have as I have already told you, that it is little bit difficult, but it gives you more accurate result. So this method is going to give you more accurate result, but the trade-off is that it is little complex to calculate. So how we'll calculate it? So you see, the total current, again the same formula. So we know that our I is equal to nothing but C dV by dt. So this is the basic equation of your capacitor current. Okay, so the current which is passing through the capacitor. And you see that let's say for time being, if we consider that the output is like charge initially and it is falling. Okay, so we want to determine V, the output is V at VOH and now it is falling. So we have to determine tau PHL, okay, high to low. So let's say in that case our PMOS will not conduct, okay, so NMOS will conduct because capacitor is already charged to some value, that is the maximum value. So VDD, it is charged to VDD, which we denote by VOH. Okay, so ID will be 0 because PMOS will not conduct in this case. As your input becomes 1, okay, then the PMOS doesn't works, okay, and your NMOS works. So let's say NMOS is working. So when NMOS works, at that time NMOS starts working, PMOS becomes off. So during that situation, what will happen? Your capacitor, output capacitor will start discharging through the NMOS. So there will be only the current through the NMOS. In the previous equation, as you can see, that we have written the collector current, okay, or the this capacitor current, not the collector current but the capacitor current. So that capacitor current is nothing but the difference of the PMOS current and the NMOS current. If you'll apply the KCL, then you can easily see that this KCL is very important. Okay, whenever you have to solve a numerical, you have to apply the KCL as well. So this KCL Kirchhoff's current law becomes very important. So you have to just apply the KCL to an inverter, and you will see that this equation is, follows. So IC is equal to IDP minus IDN. Okay, so if IDP is equal to 0, so obviously your equation will become C load, okay, capacitor, this load capacitance into dV out by dt is equal to minus of IDN. So now you see, keeping this into mind, if we see the equation and the regions in which the circuit will operate, so let's see. So let's jump into this details. So you see, our input waveform is, you can see the input waveform in the upper graph. So VOL is your initial input, and later on it is becoming VOH. So your transition takes place when input changes from VOL to VOH. Okay, and as I have already told you, that we are considering the ideal input waveform. So that means it doesn't have any rise time. Okay, so if it doesn't have any rise time, then the output will start to change as soon as the input has changed. So input is becoming VOH and now the output starts changing. So as the output starts changing, so you see, initially what will happen? Our NMOS will be in a different region. Okay, so you see, if we see our NMOS, so NMOS will follow which equation? See, for NMOS, this input is becoming 1. So obviously the input is greater than its threshold voltage. So first condition, which is the input voltage or the VGSN should be greater than VTN. So that is satisfied. Now we have to check the second condition. So in this, if you check the second condition, then you will find from this particular thing that if our output is VOH, initially it is VOH, and input is also becoming VOH, so at that instant, if you will see that, you see, gate to source. So here if you will see, if you'll see, so gate and our source. So the input is VOH. So VOH minus 0. So the input is VOH, right? And output drain is also connected at the same instant to VOH. So drain to source is already grounded. So drain to source voltage is also VOH and gate to source voltage is also VOH. So you see, whenever this gate to source voltage and the drain to source voltage are same, the device always works in the saturation region. I have already told you this. But if you'll check the equation that in which region it operates, so you can easily see that in this case your VDS is equal to or will always be greater than VGS minus VTN, because VGS is equal to VDS, so if you'll subtract something from VGS, then VDS will always be greater than VGS, right? VGS minus VTN. So you see, that is why your transistor will operate in the saturation region initially. So this is very important, because this is what you will require later on. Whenever you have to analyze the circuit, you have to just determine that in which region our transistor is operating, whether it is operating in the linear region or it is operating in the saturation region. So once you are able to find it, and if you have find it correctly, then there is nothing, okay, then it is just the mathematical manipulation. Then you should know the differentiation and integration very well, whatever you have learned from your schooling and all those things. So you have to know those things very well. So if you know differentiation and integration, you can easily solve the equations. So the most important thing is writing the correct equation, and you can write the correct equation only if you have determined the correct region of operation. If you made any mistake in determining the correct region of operation, then obviously everything will be wrong later on. And you see, the same thing what you will do here in the derivation. Sometimes you can use directly the formula, but it will, I'll suggest you that you always go from the basics, okay, always start from the basic, and don't remember just the formulas, because there are assumptions while deriving the formula, and in a particular problem you may not, the assumptions may change, the input conditions which you are assuming for the derivation may change in the problem in a particular design scenario. So it's better to start from the initial things, okay. If you know your concepts well, then you can derive the things very well, that's not a problem. So you see, my suggestion is that now you see, as we have determined that our NMOS operates in the transistor and the saturation region in the up to a certain voltage. So at VOH it operates in the saturation region, but it keeps on operating in the saturation region till your output voltage is greater than VOH minus VTN. Okay, the reason is same. This VDS should be greater than VGS minus VTN. So your input is VOH, okay, and your output is now falling. So as soon as it becomes VOH minus VTN, now you see it will later on after this point, VOH minus this output will be less than VOH minus VTN. So you see, your transistor later on will start working in the linear region. So the transistor NMOS will work in the saturation region from VOH to VOH minus VTN, and from VOH minus VTN to later on it works in the linear region. So that should be very clear to you. There should not be any doubt in this. Okay. So now let's say on the time scale, if we denote this various times, so we can write that the initial time as t0 when the transition is starting. Okay, so the starting of the starting of the transition, let's say that is denoted by t0. Okay, later on when till the time it operates in the saturation region, we denote that time by t1 dash. Okay, and later on let's say at the 50% time. So because we want to determine tau PHL, so tau PHL is your this starting from the 50% of the input transition to the 50% of the output transition. But as our input is transiting at an instant only, so that 50% will be equal to, there will no 50, that 50% will be at that instant only. So you see, this is how you have to determine this tau PHL. Excuse me. So you see, so your tau PHL will be this. So our aim is to determine the time elapsed between t1 to t0, but that time is actually divided into two halves. So first we have to determine the time from T1 dash T0 to T1 dash, and then later from T1 dash to T1. Okay, so you see between T0 to T1 dash the transistor operates in the saturation region, whereas from T1 dash to T1 the transistor operates in the linear region. So keep this into mind. Now if the transistor operates in the saturation region, then we will use the saturation region equation, saturation region current equation. Okay, so you can see that first of all for the particular condition we have used the topmost equation. If you will see, we have used the saturation current equation for the NMOS, and now this equation, because we want our this point, okay, so we have to differentiate this. So if you differentiate this equation, this integrate this equation, so you will see that because we want the transition from T0 to T1 dash, so you have to integrate it. Okay, so if I integrate this equation, then you can see that I can write it in terms of this capacitance equation, and in the capacitance equation if I substitute this particular I which we have seen earlier, so you can see that C dV out by dt is equal to minus IDN. So in this equation our aim is to substitute IDN. Okay, so if I substitute this IDN in this equation and integrate it over the range from T0 to T1 dash, then you can see that the integration limits will be on the left side it will be from T0 to T1 dash, on the right side it will be from VOH to VOH minus VTN. And if you integrate and substitute these things, it's not difficult, you can do it by your own, but you can see the calculations and you can see that your T1 dash minus T0 will be something like this formula. So this T1 dash minus T0 will be twice of load capacitance into threshold voltage of NMOS divided by Kn transconductance parameter, process transconductance parameters of NMOS into VOH minus VTN whole square. Okay, so this is very simple. So now you see this is our first half of this. Now in the other half we have to determine the time elapsed between T1 dash to T1. So first of all we have determined the the time elapsed between T0 to T1 dash. Now we will determine the other half. Okay, so you see, to determine the other half, as we have already seen that our NMOS operates in this particular region from T1 dash to T1 in the linear region, so we have to use the linear region current equation, whereas the other, this capacitor equation, because the capacitor is discharging, so it will be same. Okay, so there is the capacitor equation, you have to use the same capacitor discharging equation, and then to use this drain current equation. Now substituting again the limits of the time and the voltage values. So you see the voltage is now we have to substitute from VOH minus VTN to V50%. Okay, and the time you can see on the left half of the equation, it's very clearly seen. Now if I magnify it and can see it, so you see it's not difficult to understand. Now again same procedure, if you substitute the value and integrate the equation, okay, then you can find that your T1 dash minus T1 minus T1 dash, again in terms of load capacitance, VOH and VTN, okay, and the transconductance parameter. So this is our formula for T1 dash minus T1. Now if you have to find the total capacitance, this total propagation delay tau PHL, then what we have to do is we have to sum them up. Okay, so tau PHL is nothing but the sum of this previous two equations. So this equation T1 dash minus T0, what we have determined here, and the sum of this T1 minus T1 dash equation. Okay, so if you sum them up together and if you see this equation, you can easily see that this particular thing, so tau PHL is, we can see from this equation. Okay, so this is how your equation will become. So tau PHL is C load upon Kn into VOH minus VTN into twice of VTN upon VOH minus VTN plus log of, okay, this all from calculation you will see that it will become 4 VOH, because this is like sum, so it will become this two terms, okay, sum of these two terms. So V50%, you can can see this. Now, if you substitute the special case when VOH is equal to VDD and VOL is equal to 0 because it is a CMOS inverter. Okay, so tau PHL, this previous equation was a general equation, and for a CMOS inverter, if you'll see that VOL will become 0 and VOH is equal to VDD. So you can write the equation in terms of either VOH and VOL if you are using any other components, but you can write it in terms of VDD and 0 if you are using a CMOS inverter. Okay, so this is how you determine tau PHL. It's very easy, it's not difficult. Okay, and I have skipped the intermediate this mathematical things, but if you have any doubt in this thing, you can ask me, I can clarify the things. Okay, if you have any doubt, we'll clarify it later on. You have to just put me the queries and I'll answer those queries to you, or we can take an extra class there and then you can understand them things. Okay, so okay, fine. So if now we want to find tau PLH, then we have to follow the same procedure. So following the same procedure, you can find tau PLH as well. So this is how you determine tau PHL and tau PLH. Okay, so this is the case. Now the other case is when the condition is let's say symmetrical inverter. So symmetrical inverter, for a symmetrical inverter you want to determine, so you have to substitute the conditions for a symmetrical inverter. So symmetrical inverter, for a symmetrical inverter you know that VTN is equal to VTP and Kn is equal to Kp. Okay, or Wn Wp or Wn by Wp is equal to mu p by mu n. So you can substitute those things and can easily determine that. Okay, so probably this is up till here. So we stop our today's class here, and in the next class we will see the numericals based on this, particularly what we have derived today in the today's class. So you just revise these things. In the next class I'll take the numericals based on this, and then later on in a few more classes we will do the remaining things. So thank you to all of you for listening. Thanks.